Hello everyone, this is another ABAQUS tutorial. In this tutorial, I'm going to simulate a steel beam column joints to evaluate the behavior of the welded beam column joints. The material we use in this simulation is steel Q235, which has a yield strength of 235 megapascal. So we will see some failure behavior, which usually I call shear failure, and the shear failure is 0.5% of the yield strain, and the column size is 200 by 200 and 50 millimeter thickness. So it's called a box section. The beam is also a box section, but with different diameter, so 150, 120 and 20 millimeter thickness. Then we will apply a boundary condition in this region, and in the end of the beam I will apply a load. So the load will be as a push, and just we will push by 20 centimeter, which is equal or almost the size of the width of the or height of the column. And you also can do it using other connection, such as weld connection or end plate connection. But just for simplicity, how you can properly model this behavior, consider just the connection. We go to the ABAQUS. Here I have already modeled, but I want to show you from the sketch, and I'm going to select here, rename it. Okay, just going to model 2. Create a model. I can here I can take a new one, and that's already saved, and I want to create the first column. And column, we can use solid elements and also beam element, but for better understanding, just I want to use shell element. Using shell element extrusion, and the first I want to give the size of the rectangle, which is 200, so it's b minus 100, or even I can, without giving the number, I can draw a rectangle and give the dimension. So this is 200 and 200, and the length is 1000 millimeter or 1 meter. So the second part is beam, and the same method, and the size is 120, and the height is or depth is 150. The same dimension or length. We finished, and we go to the define material. The material I have here, the material in my library, I'm going to add it, and you can see what is the properties. Even you can check in the or Google it, you will get this properties material. The density is, because I want to consider some failure criteria, especially I will consider the shear failure. So the shear failure just supported by explicit analysis, so that required to conduct a dynamic analysis. For the dynamic analysis, we should provide the density for the material, 7.85 E minus 9, which is Joule per cube meter, and the elastic modulus is about 119, and you can also take it to 100,000 megapascal or 200 gigapascal. So the Partition ratio is 0.3. The plastic is I also considering some degradation. Here you can also consider that's also allowed in ABAQUS, and ABAQUS can support this. And this is almost the behavior of the steel. So the steel curve first start in the elastic region and then go to the plastic, and then again a little degradation, and then it quickly drop down. So we can consider that degradation as well. In some tutorial, just we consider until this area, but it's approximately true to can consider this as well. So I will take this one. In case if you have any doubt about the result, you can delete and you can check this area and again add these parts and compare the result how this behave. Now it's okay, and we want to define two sections. One is for column, which has using shell element homogeneous, and it's 20 millimeter for the beam. Beam is 15, yeah, so that should be 15. I'm going back to here, and that should be 15. And the second one is for beam. This should be 20 millimeter. The same material. Now we created this two section. I'm going to assign it. This is beam, and I'm going to add beam. The second is column, and I want to add column. Now it's okay. We created both material, and before go to the assembly, I want to create some partition for the column because during the meshing and the contact, there will be some little distortion in the joint in that joint. So I want to prevent that distortion and also some disconvergence. So it's better to create some partition and create that specific line which is passing in the other elements. So I'm going to select this one here called partition face. I'm going to select this face and just enter and take this line. So now I know the size of the one I want to give this line to this line here, and one again this line to this line, and the depth is 200, but the depth of column is 120. So I'm asking to these two should be 20, and these two also should be 40. And so now I can measure this 2 point is 120. So what's next? I'm going to give one here and one here. Now I can take this one. The total length is about 1 meter. Take this dimension, and the total length is 1 meter. So we have the height of the beam is 150. So when we divide it by 2, then it become 250. So this should be 250. So, and I'm going to use the same for here, 215. So the total become 850 and 115 is left. If I go to this one, 150. And now we created, this is 150 and this is 120. This is 120. Now I can, so some area is over dimensioned. I'm going to delete these things and it will be okay. Now we can see we created a very nice partition. Now I can go to the assembly, and I'm going to bring a beam column, and I'm going to use this offset to be out of each other. Now the next I want to rotate using this dimension. this location, and one more using this. That should be 100 minus 19. That's other side, and I'm going to select it again, and this time I'm going to give 180. So it will be selecting this one and asking 100 180. So this is the correct, and I want to bring rotate the beam as well. So this is the beam. So one, you should take this one, and again going to be here. Okay, and this time select this one and selecting this one more. Instead of giving 118, I'm going to back here to give minus 90. And now I can use the translate option, and I'm going to putting this point to this point, so exactly in the right location. Now I can go to here and see it's correctly adjusted. I'm going to move all and selecting that point to 0, 0. Now here is we finished in the assembly. We can go to the step. So I want to conduct a dynamic analysis, so I want to call it dynamic. In the dynamic, I want to use explicit, and here is the explicit dynamic. The method which I want to use is looks like static, which the time period is about 1 second. In case if I use a very short period of time, that means that's quite fast and seems dynamic. But in 1 second, it means I apply the load slowly. Even I can increase to 5 seconds. As much as I increase the time period, so it is changing the behaviors from the static and from dynamic to static. So other parameter is as it is or default, and next I want to create some a reference point. I want to create a reference point here, and this is first creating some data point and to find out the center of that column. And now I want to define the reference point. So this is the reference point 1, which I want to apply load in this point or the end of the beam. And this is the in this region I want to define some stiffener, which I will restrain this area. It means we are not discussing above of this area, so we want to totally restrain this area, and we not allow any deformation in this area. Just we will consider the deformation across this joint, and specifically this area which we considered as a weld. I'm going to back in assembly. We're not using some contact. Even we can use tie or even contact, surface to surface or node to node, but there will be some instability in this area which will not solve our problem. But instead we use merge. That means that giving us a very manufactured style for the beam column connection. Looks like 100% fixed and rigid. So when I call it beam column joint, giving retain it and geometry, and I'm going to select this one and these two. Now we made that both column beam in a single element. Now again, because during the merge so the other data will remove. So I should redefine the 3 points and 3 reference points. Okay, now here is reference point and the first reference point and the second, and now we created them, and I want to define a seed. The seed is called loading point or loading. So this is the loading, and we go back to here. We defined the steps, and we consider that default output, so that contact is no need, we can take it, and the interval can be, let's make it 200, and here is the output. I want to create an output using that set loading, and here I want to get as in 200 from 200 interval, give that displacement in the vertical dimension and the actual force in here. Instead of applying some concentric load, we'll apply displacement. So we push until the total disconnection fail. So then we will measure the displacement. So when we apply the displacement in this point will create reaction force. So just you're taking your finger, you're pushing some specific location, and there will be vertical reaction force on your finger. So that means when we are applying the displacements, you will get reaction force. When you're applying load, then you have to get the reaction force from the boundary condition. Okay, we will select the displacement in U2 and also RAF2, and okay, now we created the displacement as well, and the last one is going to the load, sorry, interaction. In interaction, what I said, we want to restrain other 3 parts because we are not considering the top of the column or bottom of the column, just we want to focus on this region. So that means we want to restrain and create some sort of stiffener in these 2. So you can use tie, you can use rigid multi-constraint point, or you can use coupling. Any of them is okay. So I will use I want to use multi-constraint point, and you can use tie. So let's see what will be the difference. I'm going to select that point, and that point is a master point, and other edge is the slab point. So I'm going to select it, okay, here like this. That multi-constraint point means we creating a rigid diaphragms in that area, so the deformation is not allowed. Now we can go to the second and selecting this point and this area. So in the result is out, you can see there is no deformation in this area because our focus is in this beam column joint. Now the third one is also multi-constraint point, and here it is. Now we created. The next thing is we want to go to the load. In the load, we want to apply a fixed boundary condition in this area. In caster. So because we will not allow any buckling of this column, and the column is quite strong, Next, we want to apply a loading as a displacement here. Selecting this point, or you can go to the state, taking that point. So now it's in D. I'm going to use a minus 200. So it requires some amplitude. You can go to in the 0, 0. In the 1 should be 1. So it means in a time period of 0 is 0. When it reaches to 1 second, so it will take this 1 amplitude times to this 200 millimeter. Now here I can select. Here is the load is applied. Now we don't have anything else, and just we should apply the mesh. Here in the meshing, we want to create a fine mesh. Even you can select these elements, these elements, these elements using a fine mesh. In other element should be coarse mesh. It doesn't matter, because the most important area is this area. So this part here. Now we can say mesh yes. So the mesh is totally uniform fine mesh. And now here is the element type, and we should define the explicit method from here. And there is one more thing in the integration factor. When we have especially beam element and also shell elements, there is some integration point across each element. So now this is one element. In each element there is 5 integration point. So that 5 integration point means we integrating in each question 5 times. So that needs a loss of time. So we can check reduce the integration time. When the 2 integration point is same and program will determine, you can reduce. And one more thing, because we will define some shear failure, we want to use element relation. So we want to activate these as well. Okay, now we finished and we want to go to job. But before job, we didn't define a timeout the shear deformation. So what I'm going to do is I'm going to edit the keyword, and instead of adding in the material part there, so I'm going to add that one here in the after the elastic, and I'm put one star and call it shear failure. So you should write correctly and give 0.05%. Even you can give 0.4%, which means the plastic reached to 4%, it should start to fail. And then you can give a comma, and it will start to use these properties in the analysis. Now I can go to call BCG model or beam column join. I'm going to submit it, and you can use some parallelization, and you can use multiple processors, but mine is okay. Submit. The job is submitted, and here is the running start. So we used a very fine mesh. 25 millimeter is fine mesh actually, so it will take some time, just a while to see the result. Now it start to running, and it take some time to finish, maybe about hours or maybe half hour. So it's about 0.35 second, so we should wait for a while. Now the analysis partially completed. It took about 0.4 second, and I'm going to see the result and if there is any element relation, and that seems it didn't reach to 0.4% yield strength, but it already reached. Some element is deleted here. These 2 elements is deleted. If I shown a uh, animation, you can see exactly that top is no deformation because we define a multi-constraint point and this area, and the most stress concentration is in this region. And here finally in the bottom is removed 2 elements, and the top also, yes. So we can go to the option and let's use this option, and we can see this element is deleted. And also we can use the rendering, and this is the rendering, and we're gonna see this element is deleted. Now we can draw the curve, the force displacement curve. We can go to output, and we have created already 2 time history output. I'm going to save it as it is. Yes, we got the deterioration, and I can go to, this is a little noisy because it's dynamic, so we want to use a sort of a filter. Let's using this filter, and I'm going to give the data x, y or f, and the frequency let me give 1 and see how it looks like. So this is pretty well, and I'm going to save it as RF, and the next I'm going to use combine and taking this U1, U2 and that RF here, but I should times -1 because it's in a negative direction. I'm going to -1 times this one, and here after the comma -1 times RF. So I'm going to plot, and you can see it's in a positive direction, and I can save it called FED, force displacement curve. Now I can delete others, delete it, and just plotting this FED. So I can go to see here, and this is the response curve, which we the structure go to about 50 kilonewton. So after 55 kilonewton, it's still not degraded to 80 millimeter. We can check it in edit if there is any degradation. In between this 3 point, it's same, it's no any load increase, and between this, so it seems after this point it will degrade. We can stay a while and see the other response. So I will put this model in the description link, and you can complete the analysis and check like this and see. So we got the displacement curve, and you can use some simple mathematical equation to get the deformation or the rotational angle using this curve, taking the rotational angle. So that's all for this tutorial. Let me check the last parts. Yeah, here is the element is deleted, this element, and this element is deleted, and this element is deleted because the stress concentration is in this region. Now and we can see more. So this is the end of the tutorial. If you have any question, please put in the comment and I will find time to answer you. See you next time. In next tutorial I will conduct the reinforcement concrete under earthquake simulation.